Okay, good morning, everyone, for our distinguished webinar series in cybersecurity, sponsored by Center for Cybersecurity at UNT. Today's speaker is Dr. Ali Bidram, Associate Professor, Electrical and Computer Engineering Department from University of New Mexico. The title for today's talk is Real-Time Co-Simulation of Power Systems and Communication Networks for Cybersecurity Studies. Dr. Ali received his PhD from University of Texas at Arlington in 2014. Before joining University of New Mexico, he worked with quanta technology and was involved in a wide range of projects in the electrical power industry. His area of expertise lies within the control and protection of energy assets in power electronics, intensive energy distribution grids. Such research efforts culminated into a book, several journal papers, and top publication venues and articles in peer-reviewed conferences, proceedings, and technical reports. He is also a recipient of NSF Career Award and the University of New Mexico School of Engineering Junior Faculty Teaching Excellence Award, the IEEE Albuquerque Section Outstanding Engineering Educator Award, and also the New Mexico EPSCoR Mentorship Award, the University of Texas at Arlington NM Stelmach Outstanding Student Research Award, and IEEE Kansas Power and Energy Conference Best Paper Award. Dr. Ali, it's a great honor to have you as part of our webinar series at UND. Thank you for spending your time with us this morning. The floor is yours.
Thank you very much. Hello, everyone. Thank you very much, first of all, for inviting me. This is a great opportunity and my pleasure to have this webinar. Let me start sharing. Yeah, please let me know if you can see my screen.
It's coming. Yeah, it's good. You're good.
All right, great. Yep, as you mentioned, my name is Ali Bidram, and I'm an associate professor with EC department at University of New Mexico. We are located in Albuquerque, New Mexico, and you might probably know Albuquerque from Breaking Bad or Better Call Saul. It's the same city that we are located in. We, Let me talk a little bit about the power and energy program that we have at UNM. Uh, we offer research programs offering both master and PhD degrees in power and energy is like a track actually under electrical engineering in our department. And uh, technically in graduate level, the research that we do mostly focuses on control and protection of power grids, microgrids, smart grids, design, control and operation, and integration of distributed energy resources, power electronics, energy storage, and electric vehicles, and as well as cybersecurity of power grids, which I'm going to talk about it today. And at URA, we have this lab, which is called Power Systems Emerging Technologies, or PSET. It's a hardware in the loop lab. We use Opal-RT technology as a real-time digital simulator, and we have grid simulators, PV simulators, inverters and also protection relays, controllers, and to do power and control hardware in the loop testing. And we also have a microgrid, uh, which we call it UNM microgrid, and it's located off campus, provides power to a close by building. It's technically UNM and Film and Digital Media Department in an area called Mesa del Sol. And it has like a photovoltaic panel, has like a natural gas generator, fuel cell, and battery energy storage system, and can operate in an islanded mode. Now I'll get to the main topic of this talk and presentation, which is real-time hardware-in-the-loop co-simulation platform. So we all know that because of the grid modernization efforts all around the world, we have huge amount of communication and control technologies added to our traditional power grids, and technically they make our power grids exposed to cyber attacks, and there are different examples of that, like the Ukrainian cyber attack in 2015. To design preventive cybersecurity measures, It's very important to study the impact of these attacks in real time HIL hardware in the loop co-simulation platform. Technically, when we talk about co-simulation, we mean a platform that enables us the simulation of both power and communication networks in real time in one package. And then with that, we can have different intelligent electronic devices being tested under different types of cyber attacks or communication network conditions. So technically, we have the traditional power system apparatus, and then IEDs are added on top of that, and then the cyber layer, in this case for us, could be the communication network, protection logics, control algorithms, SCADA, and etc. So in our lab, the solution that we have used is a solution that was offered by in a collaborative effort between Opal-RT technologies and Keysight. Opal-RT, I think you're already are familiar with that. It's like a real-time hardware in the loop digital simulator. And what it does technically, when we talk about real-time simulation, we mean that if a simulation is taking, for example, the runtime of the simulation is 10 minutes, that simulation in order to run will exactly take 10 minutes. And because of that, these real-time digital simulators are equipped with digital and analog inputs and outputs and different communication ports to integrate external hardware, real hardware. And because we are running these simulations in real time, technically we can connect external hardware, power or control hardware. So power hardware, by power hardware, I mean like inverters, and control hardware could be protection relays, IEDs, or power system controllers. So we can integrate them in real time to the real-time digital simulator and then run them in real time with our simulation model. The simulation model usually in Opal-RT has different solutions, and the most like maybe practical ones are RT Lab, which is based on MATLAB Simulink and HYPERSIM, and each have different capabilities. And so we can technically model the power grid in RT Lab on HYPERSIM and run it in real time on Opal-RT simulator. But what about the communication network? For the communication network, this tool that was offered by Keysight, which is called EXataCPS, technically enables the emulation of communication networks. What does that mean? It means that Exata can handle also real-time emulation of communication systems, and because it's running real-time, it can technically handle the integration of external hardware. So we can integrate external real hardware to our communication system model in Exata and run everything in real time. So technically, Opal-RT and Exata technically can link and provide a co-simulation platform where Opal-RT takes care of the power system simulation side and EXataCPS takes care of the communication network simulation side. And then we have virtual communication links between the two to connect power system nodes to communication nodes. And also we can connect external real hardware, communication hardware to our communication model in EXataCPS and also run that in real time. What happens is that we need to have a host computer, and on that host computer we will run EXataCPS and HYPERSIM or RT-Lab, and then virtually Opal-RT and EXataCPS will connect to each other, but the actual power system model will run on Opal-RT real-time digital simulator in real time. The EXataCPS communication network model will run on this host computer, And then we can also connect the external hardware. I will explain this in more details because I'm going to talk about a specific project that we did with this tool set so you can better understand the process. The specific project that we did was focusing on secondary spot networks. Secondary low voltage spot networks are a part of distribution systems. And as the name shows, they operate at lower voltage and they deliver power to end users, like residential, commercial, and industrial customers. They are vital for powering critical facilities in highly populated areas like downtown areas. And because they're providing power to these critical facilities, redundancy for them is pretty important. So when, for example, an extreme event happens and one of the primary feeders is outage, we should have an additional path of power to that critical load. An example of low voltage spot network actually is shown here. Let's assume that this is the critical customer. For example, in downtown area, could be a police station, a hospital. And then you see, we usually have multiple primary feeders in that area. But you see here that true, and we call these technically the secondary transformers, each of these. So usually the voltage here could be at 12 kilovolts or 13.8, and then the voltage here is like the, for example, industrial low voltage 480 volt three-phase or like regular 120 volt line to neutral voltage that we use in North America at the residential level. And then you see that we have two paths, one path from like primary feeder one and one path from primary feeder two. And both of these passes will provide power to the critical customer. So actually let me use, oh,
Are you trying something, Doctor?
yeah, let me stop sharing and share again so I can use my cursor. You see the whole screen now?
Yes.
Okay, great. Yeah. Yeah, all right. Then here I can use the laser pointer. Okay, great. Yeah, so that's the whole, technical advantage of the secondary spot networks. It will provide us with this redundancy. So when, for example, primary feeder one is outaged, we still have another path to support this critical customer here through primary feeder two. And uh, the protection of these spot networks are very important. So in addition to the protection that we need on the primary feeder, which is uh, the protection like overcurrent protection, regular overcurrent protection that we can use here on the primary feeder to protect primary feeders against faults. Secondary spot networks also require some secondary protection on the secondary side, close to the critical customer. And we call them NU or NPUs, Network Protector Units. These Network Protector Units, what they do is to ensure that when a fault happens on the primary feeder, so let's assume that a fault happens here. So what happens is that this protection relay will see a huge amount of fault current and will trip. Okay. So the circuit breaker will open. But the fault is still alive. Why? Because we have an additional source of fault current to the fault location from primary feeder 2 through this red uh, technically arrow. Starting from here, we have an additional source of fault current going all the way to the fault location. So this is going to create a lot of issues. It's going to create safety issues for the utility crews. When they go there, they want to clear the fault and fix the issue. And also, we will still have a huge amount of fault current going through these two transformers, and it's going to damage them. So in practice, what they do, they add these network protector units at these locations. And these network protector units, what they do, when they see a reverse flow of current, they disconnect and trip and open this breaker here. Because they traditionally, when there is no DER, distributed energy resources, in downtown areas, the only situation that this network protector unit can experience a reverse fault current happens when we have a fault on the primary feeder. And then that's the traditional logic on these network protector units. So they operate based on reverse, technically, flow of current. And when they sense a reverse flow of current compared to voltage, they trip and open the breaker to make sure that fault is fully isolated. But you can assume, like, nowadays, like most of these facilities in downtown areas, highly populated areas, they have local distributed energy resources. And it could be photovoltaic panels, could be generators, battery energy storage systems. So what happens is that if they, for example, let's assume that we have a backup generator here, and then an extreme event happens here. So we lose the substation here, and then we want to support the load downstream of here through this backup generator. What happens is that this backup generator is going to start generating power, and it's going to create a negative flow of power or flow of current here, which here I've shown it with these green arrows. So the conventional network protector unit logic will trip and will technically stop that, because the conventional network protector unit logic is based on reverse flow of current. And then in this case, it will also sense the reverse flow of current, it will trip. So that's one challenge here. And here you can see a typical technically characteristic for network protector unit. Let's assume that here we're showing the current phasor, positive sequence of the current phasor, and the phase angle is calculated with respect to the voltage that is sensed, positive sequence voltage that is sensed at the network protector unit location. You see here the network protector unit will only trip if it technically senses a reverse flow of current. So one challenge here, I just explained it, when we have DERs, distributed energy resources, downstream of the uh, network protector units, once the DER starts to generate and has a reverse power flow, network protector units will trip. And technically, we cannot utilize the potential of having DERs in the downtown areas. And currently, that's the case in many of the utilities that are operating the distribution systems. Because of the network protector units, they cannot utilize the full potential of DERs for resilience events. And then uh, also another challenge for these network protector units are that if the transformer here has a delta side, so usually three-phase transformers are YY or Y delta. If we have a delta winding on the primary side, we cannot sense any zero sequence current. And then because of that, technically this network protector unit won't be able, because it doesn't sense any zero sequence current, cannot technically uh, detect single line to ground faults here. So in some utilities, actually, in order to avoid the first issue, the second issue, which is the when we have DERs at the load side, in order to let the DER operate and provide some reverse power flow, some backup for the existing load in the secondary network area. What they do, they desensitize the settings of the network protector unit. So you have, technically you can see that here. Yeah, they desensitize that, and then they allow for some negative flow of current. But still, it doesn't let the utility utilize all the full capacity of the DERs in the downtown areas. Another approach that can help with the utilization of DERs and also can help with the detection of the single line to ground faults that can happen on the primary feeders is to use direct transfer trip. Direct transfer trip is an approach that, as the name shows, if we have a trip command on the primary feeder relays, for example, let's assume that we have a relay here, is an overcurrent relay on the primary feeder, and that feeder can easily detect any type of fault on the primary feeder. So if we detect that fault on the primary feeder with this relay and then communicate that trip command through direct transfer trip to these network protector units, then these network protector units can become more intelligent. And then we won't have those challenges that I just described anymore. Why? Because the network protector unit will be able to rely on the direct transfer tree from the primary relay here on the primary feeder. And then if we have a DER here and the DER starts to generate and we have a reverse power flow, the network protector unit won't trip. Why? Because we don't have any fault in the system, so there is no direct transfer trip available. So the network protector unit will rely on the direct transfer trip and then won't operate if we have reverse power flow from DER. Additionally, if we have like a single line to ground fault here, this network protector unit can rely, because this relay will detect that. We won't have any issue with this relay detecting single line to ground faults on this primary feeder. And then the network protector unit will be able to rely on the direct transfer trip and will trip even for the single line to ground faults. So we can have this logic of direct transfer trip and say that, for example, if there is DERs, we have DERs at the critical customer side. In order to utilize the full potential of that DER, we can rely on the direct transfer trip and utilize that as the primary technically protection logic. And then NPUs will rely on those direct transfer trip commands and operate based on that. But what's the caveat here? Is we are going to use communication links. We're going to use communication between the primary feeder relays and network protector units. And then the issue is technically the cyber attacks. What if these communication links are compromised? So that's the challenge here. And we are going to use co-simulation platform to study the impact of these technically cyber attacks on the direct transfer trip escape. So that's going to be the focus of this talk in the future slides. So I told you I'm going to describe this co-simulation platform in more details and can see that here. So what we did, we simulated the power system model of a secondary network, exactly the secondary network with two spot networks and supporting two loads, load one, load two. And we have two primary feeders, primary feeder one on top, primary feeder two here, and with four service transformers. And we assume that we have an DER here on a spot network one. So we simulated all of these in HYPERSIM. And HYPERSIM technically model was running on Opal-RT simulator in real time. But we had external hardware. Our external hardware were two protection relays at CB1 and CB2. And we used real SEL751 relays. And then for network protector units, we technically created the logic of network protector unit on Raspberry Pis. So these are technically our physical hardware, two SEL751 relays and four Raspberry Pis, which represent these four network protector units, NPU1, NPU2, 3, and 4. So for the connection of the physical hardware to Opal-RT, because this physical hardware, these are protection relays, they need to read real-time voltage and currents from our simulation model in HYPERSIM. What we did, we used technically hardwire and connected the technically analog outputs of Opal-RT to the analog inputs of the SL751 relays. And these SL relays, some of them have these cool features called low voltage signal analog input, and through a connector which is called J2 and in some relays J12. And we can directly technically connect the analog output of Opal-RT to analog input to that J2 or J12 connector of the SEL751 and read all the measurements in real time through hardwire without any delay. For Raspberry Pi, because Raspberry Pi, they don't have any analog inputs, so what we did, we used technically Modbus communication to read the measurements from Opal-RT, the simulation model in Opal-RT. But here we tried to implement direct transfer trip scheme. So direct transfer trip means that when CB1 relay, which is this relay, for this fault, okay, for this fault location, when it detects the fault, it needs to send a direct transfer trip to NPU2 and NPU4. Because NPU2 and NPU4, in that case, they have to trip in order to avoid any, in order to make sure that the fault that we have at this location is fully isolated. And then this SEL751 relay at CB2 needs to send a direct transfer trip to NPU1 and NPU3. So how is that done? That is done. Technically, we need communication links. That is done through EXataCPS. So you see here in EXataCPS, we have a model of our communication network. Yeah. For all the nodes that we have in our system, could be physical hardware nodes, actual physical hardware, or the nodes that are available in Opal-RT HYPERSIM, we can create a virtual node in EXataCPS and connect those virtual nodes to the actual IP addresses that these devices have. That's how the connection between the communication network model and physical system model or simulation power system simulation model is performed. And then here in EXataCPS, we have another cool feature. We can define the communication media between the nodes. For example, what's the communication between this SEL751 relay and this Raspberry Pi? Is it through radio? Is it through like hardwire? Is it through wireless communication? And is it through fiber? We can control all of that. We can control all the communication specifications between this SEL751 relay and Raspberry Pi through EXataCPS. And then it has some other cool features. For example, we can map it through a geographical area. And then, for example, if you want to test radio communication in that geographical area, you have some hills that can block that radio communication. We can map this on that exactly same area and then see the impact of, for example, high buildings or high hills on the communication between these two nodes. And the other cool feature is that on each communication link in EXataCPS, we can model different types of cyber attacks. And that's what we try to use here. We wanted to study the impact of cyber attacks on the direct transfer trip scheme that we use for the secondary network. The cyber attacks that we tried were uh, the first one, packet modification attack, which is technically like false delta, the false data injection attack, and that we assume that the packet modification attack can take control of transmitted signal, which is direct transfer trip from SL751 relay to Raspberry Pis, and then deliver corrupted value. There are two ways to do that with with EXataCPS. We can either replace, because direct transfer trip is a very simple signal, is either 0 or 1, because we either have a trip scenario or we don't have a trip scenario. If we have a trip scenario, it means that we have a fault, then direct transfer trip signal is 1. If we don't have any fault in the system, direct transfer trip signal is 0. That means that we are in normal system scenario, no fault in the system, so then NPU should not trip. So we had two ways of implementing that. We can either replace the value, for example, if direct transfer trip signal is actually 1, and we want to model the cyber attack, we can replace it with 0, or we can inverse it. Actually, there is also an inverse feature that we can inverse, like toggle it from 0 to 1 or 1 to 0. And both of these approaches technically render same results. And here is technically an example. For example, assume that there is a fault in the primary system. When there is that fault, DTT will be equal to 1 because the primary SL751 relay can detect that fault. But we simulated this packet modification attack and replaced the value with 0. And then NPU, technically what it read to the communication link, what it received was 0. But we had a fault. DTT was actually 1, but NPU received 0. So we see that NPU is not going to trip in that case. And then we still have the the fault. Look, even though the primary feeder relay is isolating the fault, but NPU doesn't trip, so the fault will be technically still alive through the other paths. The other type of attack was DOS attacks and denial of service attacks. With EXataCPS, we're able to do two different types of DOS attacks. The IP fragmentation, which aim at exhausting the target's resources and disrupting the service by sending packets in fragments. And then technically this attack forces the packets to wait in buffer until fully reassembled. This leads to an overload of the target CPU buffer. And in our case, our target are technically our NPUs, which are modeled on Raspberry Pis. And this can technically result in a system crash. The other one is the TCP synchronization attack, and it's technically taking advantage of the handshake process in a TCP connection. So attackers start sending a large number of SYN requests, SYN packets to the target server. In our case, the target server is technically the Raspberry Pis. And then uh, so the attacker starts sending large number of SYN packets to the target server and then responds to each request and opens a port to avoid the client's acknowledgement packet, but this acknowledgement never arrives. So the attacker continues sending these synchronization packets and causing the server to keep allocating new open ports temporarily, and eventually this exhausts the server's available ports, leading to a server malfunction. Here I've shown you some of these scenarios that we ran. Okay, so the first one is no fault in the system, but there is a packet modification attack. When there is no fault in the system, this is for case A. See that here. So the DTT signal should be technically 0 because there's no fault in the system. But look at this orange one that NPU2 has received. You see NPU2, instead of receiving 1 after the cyber attack is applied, is receiving 1. So it is going to mistakenly trip, and it's going to create an overload for our service transformers in the secondary network. So this is a pretty bad situation. Then the second scenario was for packet modification attack. We had a single line to ground fault in the system, but no cyber attack. So everything was okay, and all NPUs operated properly and correctly. But let's assume we have single line to ground fault, but with packet modification attack. So what happened was that the attack was applied between the SEL751 relay and NPU2. And you see, even though the DTC signal is asserted to 1, but NPU2 doesn't receive 1. It receives 0 because of the packet modification attack, and it doesn't trip. Then we also repeated these cases with three-phase faults and saw the impact and the issue. Then IP fragmentation attack results. IP fragmentation attack, here we assume that we have a single line to ground fault that was applied on the primary feeder, and then NP2 was the victim of the IP fragmentation attack. And then here, this is with mobile extern, we were monitoring the operation of all 4 Raspberry Pis. So, and as I mentioned, each Raspberry Pi technically emulates an NPU. And then you see here that NPU2, which was the target, started to fail. Technically, NPU2 crashed, and because of this IP fragmentation attack, and then couldn't continue the operation. So you can see that obviously here from the mobile extern and the Modbus communication, which was responsible for sending the transfer trip signal from SEL751 to Raspberry Pi failed. Yeah. And then here is an example of the TCP synchronization attack. So same as the previous scenario, we applied the single line to ground fault, and our server here was the SEL server 51, which was sending the technically direct transfer trip, and its IP address ending in 122. And this was the victim of the TCP synchronization attack. It tried to send the direct transfer trip signal to NPU2, but we use Wireshark to traffic the monitor, and then we noticed that after the attack was applied, this TCP retransmission error occurred. TCP retransmission occurs when an acknowledgement of a transmitted packet is not received by the sender with a specific time frame. So technically, an NPU2 never received the direct transfer trip signal in this case from our SEL751. All right, great. So I think I can now summarize some of the observations that we have. So obviously we saw that for direct transfer trip, even though it's very cool technique, it will remove the challenges that we have with network protector units. With direct transfer trip, technically we can let DERs have reverse power flow and support other loads in the highly populated areas. And also they operate perfectly for single line to ground faults. But the challenge is cybersecurity. When the communication links in the secondary network area between the primary feeder protection relays and NPUs is corrupted. Could be different types of attacks. We showed that for all, technically we simulated three different types: the packet modification, IP fragmentation, and TCP synchronization. For all three scenarios, we noticed that the NPU operation will be compromised when the communication links are exposed to these cyber attacks. So that's a big issue. And uh, so what's the solution here? One solution could be that we still rely on some backup protection logic at the NPU. And that backup protection logic could be based on the conventional NPU logic that I showed you here. But the problem is that this one also had some challenges and issues, but still we have some basic protection at the NPUs with this approach. But this requires, and this is technically the research that we are trying to do at this point, this requires attack detection techniques and mechanisms. And so we can detect these attacks technically fast enough and then take appropriate actions because before the performance of the network protector units are compromised. And technically, this code simulation platform that we had with Opal-RT and EXataCPS helped us study the impact of these attacks. And later, when we design mitigative actions for network protector units, we can test them again under with this technically hardware in the loop testbed that we have, and then see if those mitigative actions are working or not. So I think that was it. It was my presentation. Let me know if you have any questions.
Thank you, Dr. Ali. We'll take some questions, but can you go back with your Opal-RT setup, and then that may be a place
Yeah.
that have more questions. While we wait for question, maybe I can start with the first question. A couple of things. The attack editor that you talked about, where is it located? Is it something that you guys programmed, or is it something that is coming? Where is the attack editor?
Oh, the attack editor is here. So you see, this is the technically interface of EXataCPS. And then EXataCPS, we run it on our host computer. And then you see we have these communication links, yeah, defined between different communication nodes. In order to apply the attack, we just can click on each of these communication links and do right click and then uh, uh, open the attack editor. And then after we open the attack editor, we can just define the type of attack.
Uh, you know, um, You talked about deceiving the NPU. Have you tried, or your team have tried something on coordinated attack to deceive the NPU? Have you tried anything like a coordinated packet modification or some other attack scenarios?
No, we haven't done that. Yeah, that's a good point. Let me write it down to coordinated packet. Yeah, that's a uh actually first we need to see if we can do it with Exata, but yeah, let me write it down. Coordinated attack. Yeah.
Okay, we have some questions coming in, and folks can even ask, and if they want to ask some questions, make use of this opportunity. So let's see. There's a question from Dr. Mona Lisa. DTT is applicable once we have fast and dedicated communication channels, such as fiber optics, but without open network involvement, such as cloud, cyber attack is not possible. Please, can you help in this context?
That's right. So DTT technically is coordinated through fiber optics. Usually, what we have in these situations, there is this technically network switch from Ethernet, which is called vault guard. And then what this vault guard does is connected through fiber optics to protection relay and also to uh, the network protector units. And as you mentioned, like uh, technically the attacker, in order to get access to the communication links, you need to either use the protection relays because they also have ports, or they need to use this vault guard and then get access to the communication links. So it's not true cloud, yeah, it's through fiber optics and these vault guards that provide the technically vault guard is like a network uh, switch that is specifically designed for network protector units and connects technically network protector units, multiple of them. So let's assume that we have an area, they put a vault guard there, and then they connect the protection relays, that SCR relay, to multiple of these network protector units through that vault guard.
Okay. Other questions?
Okay, so I want to ask the question. Would you mind go back to slide number 9? And in this system diagram, I'm initially I sort the NPU. That's actually it's a even though it's called a network, but I sort that network initially should be different from the Ethernet. However, afterwards you show that the NPU indeed has a packet, IP packet, shows up, and so I'm not very clear about the system structure afterwards. And so that's one of my questions. I feel that it should be two different kind of the network really gets covered. And the second question is that for the type of the attacks you have raised, like the denial of the service attack happens over of the during making TCP connections. Well, I think, during for establishing TCP connections, the timeout value usually set to be very short. So it may not be, a good case to say, the denial of the service attack will be able to make it possible because of the very short timeout. Whenever timeout happens, the connection gets, abandoned right away. Unlike for the application layer of the protocols like in HTTP. Okay, so in that case, denial of the service is possible because there is generally no timeout value gets set. So, for the study also like IP fragmentation attack, I would say that the overhead for even be able to dynamically generating or modifying of the packet in that way, okay, so it may not be able to quickly inject, okay, of the large volume of the attacking traffic. Okay, so that's what my question is about. Thank you.
Yeah, thank you for your question. You're right. So technically, we have here two technically communication network. So this one that we have modeled in EXataCPS is technically the communication between SEL 751 relays and Raspberry Pis. And each Raspberry Pi, when we say network protector unit, we refer to the power grid network, not the communication network. And uh, technically, yeah, I know it's a little bit confusing, but the network in network protector unit is not the communication network protector, it's the power grid network protector. That's I know it's confused. It's confused is the name that they have used in protection society for those specific relays. They call it network protector units. But it's totally separated from communication network. And then regarding the other question, yeah, you're right. That depends on highly on the timeout, especially for the denial of service attacks. But the application that we're also targeting here is very critical, and protection systems are required to act super fast. And like, for example, in this case, we are talking about milliseconds. Yeah. So if the network protector unit doesn't act within milliseconds, that can create huge issues for those service transformers. So it's a matter of the comparison with that timeout and that required time for the operation of the network protector unit. Because if we put some delay on the operation of network protector unit, then you're right, then that issue technically, the denial of service attack issue won't matter. But then here we have a trade-off between, do we want to overload our service transformers with huge amount of fault current for, I don't know, that like few seconds or not? Because over time, technically, that can damage the service transformers.
I see. Thank you.
Yeah.
Thank you,
So,
Dr.
once again, for the NPU, so it is a different type of it still communicate, okay, but that protocol may be quite different from the Ethernet of the protocol. But in the in that type of the network, whether it still have the concept of the packet or how the information gets transmitted in the other type of the network. I'm outside of that area, so I'm unfamiliar of that technology.
Yeah. So let me tell you, so all network protector units, they are only local, and then they just have a local uh, logic based on the current and voltage that they measure. They don't have any communication port at all. Those are super old network protector units, and they still call them network protectors. Newer network protector units, like from Eaton, Eaton is major player for manufacturing these network protector units. They come with communication ports, and those communication ports support Modbus and DNP3 communication. And that is also, I talked about WattGuard. WattGuard only also supports Modbus and DNP3. So that's the common communication protocol that they have. They only have that. They even don't use like advanced ones like IEC 61850 currently. So I don't know if I answered your question.
Good.
Yeah, I try to learn. Okay, I
Yeah,
try to learn the new knowledge from you. Thank you.
thank you.
You, Dr. Janlo. I think that we have a couple of questions. We'll quickly be brief in these other questions. So for network graphs, did you consider using software-defined network for control plane and have a couple of switches for every region in the EXATA?
That's right. So in Exata, you can define as many switches that you want, and it depends on the area. Like here, because we were covering a small area, we just considered one network switch here. And as I told you, in reality, this is that Ethernet wildcard. Yeah, and that's what they do with Ethernet wildcard. They connect like 4, 5, 6 network protector units to same wildcard switch, and then they communicate to the primary uh, relays. But if we had like a larger, much larger system here with, I don't know, like 20 network protector units, probably we needed to use multiple of these. So we have that capability in Exata, as many as switches that we want, you can use.
There is another question. In terms of your IP fragmentation, TCP synchronization, DOS attacks, what parameter did you specifically use, such as packet rate, duration, target ports, to get the Raspberry and NPUs to crash or misbehave? Is it like one parameter or is it multiple parameters?
These multiple parameters, I wish I had actually. Unfortunately, I forgot to put the attack editor for DOS attack here. Yeah, it's multiple of them actually. So all of the parameters that you mentioned are available in Exata, and we can change them. Yeah.
Sure. And then I'm assuming your switches and routers are consumer grade. What do you have in a test bed? The switches and routers, what do you use?
Oh, the switches that we use, you mean this Ethernet switch?
Yeah.
This is just a regular Ethernet switch that we used. But
Okay.
here in Exata, the switch that we use to replicate this could have different specifications.
So now the question is, okay, it's all great attacks. What do we know? What specific hardening steps would you recommend in terms of mitigation? How would people should focus more on mitigation? Do you consider any mitigation steps?
That's a very good question. Like currently, so first of all, we need to detect these attacks with detection schemes. And then for mitigation, I think we should enhance our local protection logics. And then maybe just like what we're thinking of using machine learning, local machine learning algorithms. So they learn the system behavior and then uh, they don't need to rely on the communication network when this attack happens.
When you simulated the DOS attacks, there's a question here. Was it like a very all of a sudden thing, or did you do any stealthy type of modeling, variations of DOS attack types?
Unfortunately, we don't have that feature in Exata for that, yeah, for a stealth type of attacks. Yeah,
Okay.
so it's just simple one, yeah.
Super. I think that's all the questions I see. Anybody else have any other questions before we conclude? Okay, I don't see any other questions. So thank you, Dr. Ali, for your time this morning with us. I appreciate for being here. You will receive a nice flag from UND for your time, and hopefully we can find ways to collaborate. I appreciate your time.
Thanks a lot. Thank you very much for the opportunity. And it was a pleasure. Thank you very much.
Thank you.
Thank you.